Bit angle modulation is another technique you can use to vary the average voltage that goes to pins on your microcontroller or any other device that has a pin that acts as an on and off, like transistors or mosfets or shift registers. And you can use this technique for driving motors, changing the speed at which they run, as well as changing the apparent brightness of LEDs. And the neat thing about it is that you don't need any special hardware to do it. It's all done via software. It's really just a programming technique. And it's fairly efficient. You can drive one LED, or you can see here I've got 20 LEDs. And it's really not that much different from the microcontroller's perspective doing one or doing these 20. And this is just a regular Arduino development board with a Atmel ATmega 328 microcontroller on it. And usually you can't adjust the brightness of LEDs on all of its pins, all of its digital pins and all of its analog pins. But you can see here that it is possible, and it's all done with bit angle modulation. Before we get into the details of implementing bit angle modulation, just wanted to quickly show you the normal way that you fade an LED with the Arduino library. They have an example called fade, and it just shows how to use the analog right command. And you can do an analog write to an LED pin. This one is pin number 9, and you can provide a value between 0 and 255. So it's 8-bit PWM. And when you upload that, your number 9, you got to put an LED on number 9, and when you do, you'll get that. And it just shows how it can fade it with PWM. And they have a pretty nice website tutorial on PWM, and they show that as the analog write value increases, so does the length of time that the voltage on the digital pin is left high versus left low. And the longer it's on, the brighter it appears. So that's the normal PWM approach. But again, the limitation of that is that you can only do that on 6 of the pins, not all of the pins like you can with bit angle modulation. Alright, so I'll go ahead and upload my first example of an implementation of bit angle modulation, and I've got it set up to adjust the brightness of pin 9, just like the PWM Arduino example. And you can see that it's fading it just upwards. I didn't implement it so it would go up in brightness and then back down in brightness like the Arduino example had, just to make the code a little bit easier to understand. So let's talk about bytes real quick, bytes and bits. So bytes have got 8 bits inside of them, and you can get between 0 and 255 when you've got 8 of these bits to play with. And a lot of people will implement this bit angle modulation by using just 4 bits rather than using like a whole 8 bytes or 8 bits or more, you know. So you could do 16-bit or 32-bit bit angle modulation if you wanted, but having 16 values of brightness like I've got implemented here produces a pretty smooth effect. Seems to be good enough. So you'll see a lot of examples just have got the 4-bit bit angle modulation. So with that in hand, bit angle modulation is no different than PWM in that you simply hold your pin high and your pin low differently for how large of a brightness you want. The brighter you want it, the longer you hold it high. It's just done a little bit differently than PWM. What we do is we just assign an arbitrary amount of time that we would hold each bit position high and low. Again, we've got these 4 bits because I've done 4-bit bit angle modulation here. And if if you have a brightness that's assigned of 0, then all the bits will be set to 0. But if you have a brightness that's set to 10, then this bit here, we'll call this the 0 bit, kind of like I've got up here. There's the 0 bit, then the 1, the 2, and the 3. So the bit that's in position 0 is 0. The bit in position 1 is actually a 1. And so we would hold this when we're looping through, looking at the bits and seeing if we're going to turn our pin on and off. We would assign a little bit longer time to hold the pin high for this bit versus the first one. It'd be double the amount of time, in fact. These are the relative sizes of how long we're going to keep each bit on. So 1, 2, 4, and 8 units of time. And these are very small units of time. We're talking about microseconds. So any one that's in the bit position 0 will be held on for 1 unit of time, whatever that unit of time is. And if it's in the second position, it'll be held on for double that, which will be 2 units of time. And then that goes all the way down. I just showed 10 because you get a 1 here and a 1 here. So you hold it on for 2 units of time, and then you hold it on for 8 units of time. So it looks, if you graph it out compared to PWM, it's just holding your pen high and low for different amounts of time, but it just does it a little bit differently, and it makes it a little bit more efficient, and you can implement it via software pretty easily. So over to the software, I'm going to be controlling pin number 9, so I just got to define there for that pin. And then I've got a byte that I'm going to be using for a counter, and I'm going to have this count go from 0 to 15 because I've implemented 4-bit angle modulation. So this is where I'm going to increment my count each time and store it. This is the byte that I'm going to store the brightness in, and the brightness can also be between 0 and 15. And then I think, yeah, I got rid of this. We don't need this part. Increase brightness. It's always increasing brightness. And then I've just got a couple of longs here to just keep track of when I last changed the brightness of the LED. So in the setup, the first thing I do is just set the pin to be an output, and that's pretty standard fare. And then within the loop, I just grab the current number of milliseconds that the microcontroller has been on and store it in this current millis variable. And then I do this if statement, and I say if this value, whatever that milliseconds is, minus the last update milliseconds, which we haven't assigned yet, so it's equal to 0 when we first start out, is greater than 49, then go and do the incrementing of the LED brightness. So this controls the rate at which I'm updating the LED brightness. Because if I do it too quickly, then you won't be able to see this fading effect. So once every 50 milliseconds is what this is going to end up doing. We're going to go and increase the LED brightness by 1. And if the LED brightness ever goes over 15, then we'll reset it back down to 0. And when we do this update, we just have to make sure that we update the last update millis to be the current, so that it can, next time it loops around, it won't just fire immediately. We just keep this updated to be whenever we make this update. We gotta reassign whatever the last update millis was. So hopefully that's easy enough to understand. And so this loop is just running, and every 15 milliseconds it increases the brightness. It starts at 0, then it goes all the way up to 15, and then it resets back down to 0. And you can see that happening right there. It starts at 0, totally off, goes up to the full brightness, then goes back down to 0. So this happens every 15 milliseconds. This thing here though, bit angle modulation handler, this function down here, this runs as fast as the loop can run. So every time the loop runs, this thing gets run. So let's take a look at it. And I've got a bunch of comments in here to try to help explain what's happening. So every time the loop runs, bit angle modulation handler is called, and it increments band count. So we didn't assign it to be anything up here, so it started out as being 0. So the very first time this runs, band count becomes 1. And we'll come back to this if statement here. But we've got this great big if block. So we say if the band count is equal to, and I just made this in binary to make it a little bit easier to understand, a binary 1, which it does when the loop first, it does the first time this handler is called, it does equal 1. We call this other function called update LEDs, and we pass in a 0. And update LEDs, it takes a bit position. So the 0 is that bit position that we're passing in. So we'll hold off on update LEDs and let's just go look at, we'll focus on this again. So if band count is 1, we call update LEDs with a 0. Else if band count is equal to 2, all right, so the 1 has moved over 1, and that just, this is the number 2 in decimal, this is what it looks like in binary. We call update LEDs with bit position 1. And then I put a blank line here to show you that there is no band count looking for the number 3. We've skipped that one. But there is one for the number 4. This is binary 4. Else if band count is 4, then we update LEDs and we put in bit position number 2. And then 5, 6, and 7, we're skipping those again. And then now we go down to binary 8. That's what 8 looks like in binary. We do update LEDs bit position number 3, and 8, 9, 10, 11, all the way down to 15, where all of the ones are set. We're not doing anything. And now let's go back up to this if statement. So we get down to our band count being equal to B binary 1, 1, 1, 1, which is 15. And I do an if statement here. I say if the band count is ever greater than that, so we have it being 15 and then we add 1 to it, so we get 16. And 16 will be greater than 15. We reset the band count to be 1 again. And I just showed this in binary. And so we're just making sure that this counter goes between the number 1 up to 15. And again, this handler is called during every single iteration of the loop. So it's just counting like crazy, just going 1 to 15 as fast as it possibly can. But we're only updating the brightness of our LED in 4 situations. The situation where there's a 1 in the first position and there's not a 1 in any of the other bit positions. The other situation where we have a 1 in this position here, and then another one when it's here, and then another one when it's here. So only 4 times do we update the LEDs, and you can kind of see here during the cycle, you know, the first time this is called, we're going to be running this LED update for 0. And the second time, it'll be this one. The third one, we're not going to do anything to the LEDs here. And this is just implemented being able to turn on and off the pin based upon what position the number 1 is in. Hopefully you can get a sense for that. And so let's just go through the example. If we have our LED brightness is 10, and that's binary 1, 0, 1, 0. So we would want to turn the LED on for 2 units of time, and then also for 8 units of time for each one of these positions. And I just tried to show it here where we update the LEDs with the bit position here being 0. That's the very first position. And the very first position with my cursor is a 0. And that means we're going to have it off. We're not going to have the LED on at that time. So the first cycle, we have the LED off for brightness of 10. And then the second cycle, we're going to be updating the LED for bit position number 1, and it does have a 1 there. So this cycle, we're going to flip the LED on. And the third cycle, it's going to stay on because we're not doing anything with update LEDs. We're skipping that one. So we've just implemented having the LED on for 2 units of time versus that first cycle. So for 2 cycles, it's going to be on. And then we get to the fourth cycle, and that's going to be bit position number 2. So 0, 1, 2, there's a 0 there. So we will turn off the LED when that happens, and it's just going to stay off for 4, 5, 6, and 7. It's going to just remain off. And then on the 8th cycle, we will flip it back on, and it will remain on for all the remaining counts all the way up to 15. So the update LEDs function down here at the bottom, it's pretty simple. All we do is we do a bit read, and this is just a Arduino function that they give you, where you give it a byte, a number that's a byte. So our LED brightness is a byte, and it's a number that we're changing between 0, counting all the way up to 15, and we put it back down to 0. That was in our main loop here. We change the brightness 0 to 15. Just keeps on going 0 to 15. So we've got that byte going from 0 to 15, and we're going to read the bit in whatever bit position is passed in. So bit position 0, bit position 0, and then bit position 1, and then 2, and then 3. And so we're going to read that bit position, and it'll be either a 0 or a 1, and you can represent that as being a Boolean, being true or false, on or off, high or low. And so we just do a digital write on our LED pin of on or off based upon that bit position. If there's a 1 in it, basically, it's enabled. So that's it. That's how this has been implemented, and it is working as expected because we've got these cycles, and it's not updating the LEDs every single time. Okay, so now we'll just extend that example a little bit and add one little extra piece of complication, or maybe 2 extra pieces of complication. Okay, so rather than having one single LED being adjusted this time, we're going to have an array of LEDs. So I just put Arduino pin numbers 5 through 10 into this array because I want to be able to control a bunch of them and fade them up like this. And so it's pretty much everything is the same, except for I've got a couple variables here to look at the micros. So there were variables here for the millis before, just to limit how quickly we change the brightness of the LEDs. But I had to add this micros for another little trick of doing bit angle modulation. So just quickly going through the setup here, I made it just so I could put in any number of LEDs here, and then I just used the size of on the array to figure out how many LEDs that we've got. So we've got 6 of them here, and I'll use that LED count to be able to do some of the loops that I'll have to do later on. So first thing, need to set all the LED pins in the array to be outputs. So I just loop through going from 0 to whatever the LED count was, and set I do a pin mode, and pin mode you just give it the Arduino pin number and then set it to be an output or an input or input pull up. But here I'm just making them outputs, and I'm using the syntax for being able to access each member of the array. So that will give me the very first member, which is a number 5, so it'll do pin mode 5 output, and then it will do pin mode 6 output. Just count up through that. And then the loop is exactly the same. So just once every 50 milliseconds go and increase the LED brightness. If the LED brightness is over 15, set it back down to 0, and then run the bit angle modulation handler. So this is exactly the same. And the bit angle modulation handler is where I had to make one little additional piece of logic in here. And I've got a comment in explaining it. I was noticing that I was getting a little bit of flickering on the LEDs if I just did the normal BAM count increments and updates like I was in the previous example, because you need to make sure that you start adjusting these LEDs at about the same unit of time every time. It needs to be a very consistent start for doing these on-offs, on-offs. So this is, let's pretend like this line here is the start. We would, during our first cycle, we'd want to make sure that, you know, we do it on-off the way that we're supposed to. And then the next time, we want it to overlay right over top of it at exactly the same spot every single time. And if we move back and forth a little bit each time we're doing it, like this, it causes jitter, they call that. It's jittering back and forth. It's not like starting at the same place every single time. This would be way easier to show with an oscilloscope, but I don't have one. but anyways, it causes it to flicker because you're not starting things at exactly the right spot, and your brightnesses are going to start not being set the way that you're hoping that they will be set. So to make it so that we update hopefully at about the same time, I had to put in this additional if statement where instead of grabbing milliseconds, I'm grabbing the microseconds value, and I do the BAM count stuff only at a consistent micros. It has to be every 50 micros that I do this BAM count stuff. So even though this loop is running real fast and bit angle modulation handlers being called a ton of times, to ensure that it only does LED updates at a consistent time, I've just got this micros statement in here, and every 50 micros go and update the LEDs, do at least the BAM counting. So you can get rid of this if statement and just try it yourself, and you'll see that these LEDs, they won't smoothly increase in brightness. I found that it'll go from like 0, 1, 2, 3, and, you know, it'll be increasing in brightness, but then at 4, the brightness goes down a little bit. It's interesting. And then at 5, it goes back up again. And then 5, 6, 7, it's going up. And it just has to do with the way that it's jittering back and forth, and you're not giving that perfect overlay every time the way that it needs to. It needs to start at a consistent time. So that's why that micros is there. And I've just gotten rid of all the extra comments that I had here, but you can see it's pretty much the same. I changed this to be the number 15 instead of having it in binary, but everything else is pretty much the same there, calling the update LEDs with the bit position. And then the update LEDs function, there's just another for loop in here where you loop through each item in the array, and you do a bit read on its brightness, on the current, whatever the current brightness is, and then you just assign the pin to be enabled, just like before. So the only trick is, instead of assuming it's pin number 9, we got to grab the pin number out of the array and then digital write it. So continuing, a lot of people will show you that to make a nice consistent start time for doing the updates to your LEDs, rather than looking at micros like I had in my last example, people use a timer. The microcontroller, the ATmega 328, has got 3 timers inside of it, and not including the watchdog timer. You actually have 4 inside of it, but 3 of these timers, and you can use them to make sure that you have a consistent start time for doing your BAM counts, and also they will interrupt your normal program flow to perform their whatever you've got the timer doing, and you don't have to do any special coding to call this, like the bit angle modulation handler like I've been showing you, where I'm always calling it at the end of the loop. When you have a timer, you can make it so that it just runs a function at a consistent interval, and you don't have to even worry about it. It's just going to happen in the background. When the timer elapses, it'll just stop your normal program from executing behind the scenes, and it will run, whatever code you put in your timer interrupt service routine, and then it will go right back to doing what you had it do normally. So I just wanted to show you that in this example. This is the first time that I've attempted to use the Arduino environment with timers, and it was really easy to do. There's so many tutorials online, and you'll want to get the data sheet, the ATmega 328 data sheet, and it's got information about the timer 0, timer 1, and timer 2, all the different registers that are involved and how they work and how they count and stuff like that. But this is just a real quick example of using timer number 2 in order to perform the bit angle modulation. So this is some setup stuff for the timer, making the timer work in a compare match mode, and then setting the speed at which the timer runs, this prescaler, and or the speed at which the timer counts, I should say, and then the number of counts that it takes before it will cause the interrupt service routine to run. So I've got it so when this timer counts up to the number 10, that it will cause the interrupt to occur. And then this is just to actually start enabling it to call my interrupt service routine. But there's lots of stuff online where you can read all about the timers. So let me just show you the implementation of the BAM with it. So I've got the loop, and once every 50 milliseconds, I'm increasing the brightness. In this situation, I'm also decreasing the brightness, so you can see the fading is going up and then it goes back down. So just like the fade example with PWM. So this is just my way that I implemented it. If the brightness is 0, then start increasing the brightness. If the brightness gets up to 15, then decrease the brightness, and it just adjusts the LED brightness up or down based upon that. And that's all the loop does. The loop just is adjusting the brightness once every 50 milliseconds. And then the timer, because I've got it running in the background, it's going to call this ISR, interrupt service routine, once every 10 counts of the timer. And you can see I just put the BAM counter inside of it, and it's got the exact same logic as it had before, and it just calls update LEDs with the bit position, and I've got my pen, which is number 9, and I just put the bit read on the brightness and the bit position here on the right hand side. I don't need to set it to be that to equal the is enabled variable. You can just do it like that, and that works just fine too. So this interrupt service routine just is running in the background. You don't have to call it. It'll just, as the loop is executing, it might get to this statement here, and then the count the timer will get up to a count of 10, and it will just stop executing this. It will execute this, and then it will go right back to this line and start executing again. So that's the beauty of using timers. You don't have to worry about calling an interrupt, the bit angle modulation handler that I had written before. It'll just run on its own. All right, for the very last example, this is how I would go about using this bit angle modulation approach with a real project. It's an example where I've got 3 LEDs being controlled, and I just have some defines here setting which pin numbers, which Arduino pin numbers these LEDs are hooked up to. And then I've got an array here that's a multi-dimensional array. It's an array of arrays where each element in the array has got 2 items in it. One is the pin number, and then the second number is the brightness. And so this is just setting up the array and initially having a brightness of 0 for each one of the pins. And then I've got the BAM count variable here. The setup function is exactly the same. We're just setting up timer number 2 to run our interrupt service routine. And then in the loop here, you can see I've got this, instead of normal, like the normal Arduino analog write, I've got an analog write BAM, where you give it your pin number and then you assign the brightness to it. And so you can see I'm just going to assign a brightness of 1 to our first pin, which is pin number 5, and then wait a second, and then assign a brightness of 4 to the second pin, wait a second, then the highest brightness, 15, to the third LED, wait a second, and then turn all of them off and wait a second, and then we'll just loop right back up and start over again. And you can see that's what it's doing here. We're doing a brightness of 1, and then a brightness of 4, then a brightness of 15. And to my eye, I can't see the flickering, but the camera can actually see the pulses that are happening. And it's kind of neat, because now that you've gotten this far, you sort of know what's going on here. The one that's a 15, there's no pulsing on it because it's on the entire time. But these are only on for a partial amount of time. So kind of cool. But anyways, the implementation of the analog write BAM is right here. And so what you do, you have to pass in your pin number and you pass in your brightness that you want to assign. And you just loop through the array. And I've got that LED count being equal to 3, so I know how many items are in the array. And you just say, hey, is the current item that I'm on equal to the pin number that was provided? So like pin number 5 was provided here. And if it is equal to 5, then I just set the pin mode of that pin 5, to be an output. And then I update the brightness for that pin to be whatever was passed in. So you can see, to access and set stuff with multi-dimensional arrays, you just put the first item, or the first dimension of the array, and then you put brackets, and then you do the second dimension of the array. And the second dimension of the array is I should highlight this part. This is the second dimension of the array. It's the array of arrays. This is the second level of the array. And this is the item in position 0 is the pin, and the item in position 1, 0 base, so 0 and 1, is the brightness. So looking to see if in the LED array, the first item in it, or position 0, and then the first item of that, position 0, is equal to the pin number. If it is, then use that, whatever that same I is, could be 0, 1, or 2, set the second dimension equal to the brightness stored in there. And once we've done that, we know that we don't need to keep on looking, so we can just use this break to jump out of the for loop, and we don't have to keep on looking because we found the pin. And so we're just updating the brightness associated with that pin in the array when we do the analog write BAM. And that's it, analog write BAM, and we're just setting the brightness. And then our handy timer is running in the background, and whenever it counts all the way up to, I think I saw it, yeah. Whenever it counts up to 10, then our interrupt service routine will run, increments our BAM count. We've got the whole 1 to 15 logic in here, and we just update our LEDs. And so this is just modified a little bit, where we loop through the array, we extract out the pin number, and we extract out whatever the brightness of that pin is, and then we do our digital write command, just like we've done before. So hopefully pretty straightforward and a totally usable approach to using this the spam technique with your projects. So here's just another example using the spam approach with RGB LEDs. You get nice, smooth colors, and the pins here, A0 through A5, they do not have any PWM support, but you can see it works really well. I hope this is a help, and I hope you try it out. It is pretty cool, and you can just go nuts and use if you want, every single pin can be controlled with this.